I've just been exchanging emails with this Oxford academic on my quantum gravity paper that I'm trying to get submitted to journals, and he's saying that I need to give it more polish, I need to put it more into the format of what theoretical physicists expect for papers in physics. But he did bring up an interesting point. He brought up this point of neutrons and how if you put two neutrons into a 1 centimeter cube container at a Lagrange point, there would be no gravity between them. And this got me thinking. This got me thinking of yet another way of testing my idea. So yes, I mean, indeed, if you were to put two neutrons into a container at a Lagrange point, there would be no gravity between the neutrons. And that would vindicate my hypothesis, since my hypothesis states that the electron densities give rise to gravity. Neutron beams on the Earth, those do, um, those do, those are affected by gravitational fields, and I suspected that this might be a slight problem for my quantum gravity model in the first place, since well, if it's a neutrally charged particle and it's being affected by gravity, then gravity has nothing to do with charges as such. It has nothing to do with electricity and magnetism. It's just something else that's mysterious. It may still be this curvature of space time in the background, and so on and so forth. I don't think that. I think what's going on is that the electron density surrounding the Earth flips the neutron, so its up quark is always facing towards the surface of the planet, and it draws down the neutron towards the surface of the planet via exerting a force of attraction over the up quark, while simultaneously spinning the neutron such that the two down quarks on the neutron, such that that lessens their force of repulsion against the electron density, so that neutrons in gravitational fields still have mass, or still have an apparent mass there. So that's actually one issue I've had to address in the past, and it seems bullshitty, doesn't it? It seems like a little bit of bullshit way around it, just to try and get my grand hypothesis or theory to work, and it is something that's necessary. Unfortunately, it is a real consideration, and it's something I do have to consider to get this idea off the ground and to make it work. And I do need to address that in the paper. And this Oxford philosopher who I was actually engaged with via email, he's absolutely right to point that out. Yes, I do need to put that into my paper ultimately, and and talk about neutron stars, talk about neutrons at the Lagrange point, and neutrinos as well. Another prediction of my model is that neutrinos, since they're just neutrally charged fundamental particles, those wouldn't be affected by gravity at all. Or rather, they would be affected by quantum gravity in one way, and that's their flavor oscillations. The neutrinos would change flavor due to interactions with electrons from the background. They'd slam into electrons from the background and exchange Z particles with particles from the background. A Z particle is a neutrally charged gauge boson, and those would cause the flavor oscillations of neutrinos, which is another thing that a theory of quantum gravity is expected to be able to do. So yeah, I mean, maybe I could even explain gravity in neutrons via neutral currents. I don't know. Is that like acceptable, or does that sound bullshitty again? But then again, I mean, really, like when it comes to quantum gravity, what has a quantum gravity particle got to do? It's got to exert an attractive force over particles of matter. So it's got to exert an attractive force over atoms or subatomic particles or anything that can be made of atoms, right? It's got to do that, which is the main thing we associate with gravity. The dropping force. I'll drop my bloody vape. Right. It's got to do that. It's also got to reflect light, and we know a cloud of electrons would do that very readily. So electrons at the moment already seem like the front runner particle. I think. And I don't think it's too much of a stretch to say that yeah, electrons could exert some influence over neutrally charged particles, since I think actually the beta decay of the neutron is really kind of a smoking gun for this quantum gravity idea, since a W minus, is it, or W plus is exchanged? No, hang on, it turns into a proton. Okay, so it's a W plus, yeah, that's exchanged from the background with the neutron, and then an electron is emitted, or in the process of that happening, a background electron is what I would say is released, is liberated from the background, and that travels off into space along with an electron, an anti-neutrino, right? An electron anti-neutrino. So, and then the neutron becomes a proton, and that's, yeah, I think that's a good way of proving that electrons do have something, you know, do play a very important role in gravity, because the thing I really don't like about physics is just the bolting on. I hate the bolt-ons of new particles. There's new phenomenon. Oh, we need a new particle. Like, oh, yeah, X-17 particle. We need a new force of nature. Like, do we really, or have you just not figured out the configurations of standard model particles that you could use already to explain this new phenomena? What was my answer about the X-17 particle? I'll have to go over all that again. I can't remember what the X-17 particle was. It was something that emerged at 17 mega electron volts. I suspected it was an electron and a positron, which were failing to annihilate one another because there's a photon of a certain energy level trapped between them, creating like a film of photon fluid that is neither being swallowed by the electron, and the electron's disappearing to somewhere else for that reason, and or the positron. But I don't believe in positron, though. I think they're W plus particles. So really, what it is a photon getting in the way of a W plus being absorbed by an electron, and that is my answer to it. And I need to somehow come up with an answer for the W plus and minus particles mass being concomitant with that idea, and having lower than giga electron volt masses, since they've been detected in particle accelerators and bubble chambers, and their masses have been measured. But I want to because a lot of the processes that I describe in nature, mass is a product of charge and electrical potential energy. So if you have a W plus and a W minus near to one another, their masses cancel out because they exert an exactly equivalent mutual force of attraction over one another. So they don't have mass in that instance. They're massless particles, which means they can shape shift, and they could be a shadow particle or something, if you like, or a chameleon particle. Have you ever heard that phrase before? Chameleon particle? That's that's an interesting way of describing, I think, those sorts of interactions, those sorts of exchanges. So, for instance, there's W plus in the case of the X-17 particle, with the electron and the positron involved in that composite. The photon in the middle doesn't block the force of attraction between them. So this W plus, which would otherwise have a very great mass, its mass is being lessened by a force of mutual attraction in much the same way as the force of mutual attraction between the W plus and the W minus during the gauge field exchange of particles between an electron and a proton, between an atomic nucleus and an electron, right? This gravito-electroweak exchange of particles. In much the same way, it it lessens the mass of the W plus, right? So again, no positrons in this model, just W pluses, and different manifestations of the W plus and W minus particles. And with positronium, which has been created for all of, I think, 142 nanoseconds or something like that, or a sixth of a second. I think there's microseconds above nanoseconds, I don't know exactly, that might be the same number, I don't know. But they appear and annihilate almost instantaneously or very quickly. And antimatter is very hard, famously, to keep stable. So what I'm also closing in on is something that's called the baryon asymmetry problem, and I'm trying to do this in nice, simple, clear-cut language that's easy for everyone to understand. But I was talking to this Oxford academic dude, and he was saying that theoretical physicists really, want it in their format. It needs a lot of polishing. I think what he really wants to imply by that, in saying that sort of stuff, is like, you need to put in all the technical vocabulary that they want to hear. You need to put in all the, because I think it was actually formatted pretty much like an academic paper in terms of its actual, formatting. And I mean, he said it was a good idea though. He liked my idea. It's just another example of, like, and some other lots of them say, yeah, mate, you've got a good idea. And it's so frustrating because I can't afford a physics degree. He did also tell me to try and get a degree, and I can't afford a degree. I don't know how to get one. I don't know if my maths ability is good enough for a physics degree. I don't think it is. But then again, the sorts of maths that I'd be using would be largely algebraic and largely come down to Lagrangians and things and different, was it snatch up some of the maths that I've, that would be like basic Coulomb's law algebra stuff. I mean, that's easy, that anyone can do that. It's all the advanced calculus and the fluid mechanics and the thing like that is in danger of holding me back, I think. But I have, a lot to write about, really. And I think I need to put a lot more polish onto it, indeed, I need to go deep into this antimatter stuff, there's issues with antimatter, and explain away antimatter, because that'll be one of the major things I need to get rid of from my models. I can deal handily with protons and positrons and things. I can explain those away as W minuses, W pluses. Likewise, antiprotons, what those be, W minuses, I guess. And they're just, and antihydrogen would be, I meant antihydrogen when I said positronium before. Antihydrogen would just be a W plus in orbit around a W minus, I suspect. We've got issues to do with fractional charges and anti-up quarks, anti-down quarks. How do I start figuring out those things? Maybe I can have a sort of a model whereby we can compositize quarks with a certain, this would be how you do that, okay. you would take, say, an up quark with its 2/3 charge. If you wanted to create an anti-down quark, you need to give the up quark, right, a W minus, yeah. So it's got a whole negative charge, which overpowers, and it swallowed the W minus, and it's got the whole negative charge. So you get an apparent, down quark, which is not stable, crucially. So we take it to be, right? We take that to be a new particle, a particle of antimatter, whereas it isn't one. It's just an unstable up quark containing a doubly minus, but it's a composite particle out of a gauge boson and a fermion, and it seems to be a down quark, but it's something other than a down quark, clearly, because of how quickly it decays, how quickly it annihilates. Right, okay, and we're going from this. And this anti-down quark has a -3rd charge, and things like this, and that's how you'd be able to explain it all away, and explain things like that. I don't like doing that necessarily, because it sounds like I'm bullshitting, and I can appreciate how it does sound bullshit, and I appreciate the sound of my own bullshit, but it seems inelegant also in a lot of ways, but I think it's the only fucking way of explaining it all. I do. I do. And not just adding particles, not having supersymmetry. No, none of that shit. You don't need it. You don't need the neutralinos and the gluinos and the squilinos and the whatever else in the next particles do. Then you don't need the Higgs boson. It's an unnecessary extra particle. I'm going to do all this eventually. I'm going to write the paper and submit it again back to this Oxford dude. Run it past him again. I think he'd be amenable to it. And he's basically telling me just to put more footnotes in. Use more experiments in it. Compare it to more experiments. Use more results. Use more data. You put more footnotes in, which is very often the way to get published, is it not, in physics? More footnotes equals publish. So a lovely day on all sorts of levels. Trying to get this antimatter thorn out of my side. Still thinking about neutral currents, neutrons. I just need to write a thesis in physics, really. That's what it'll end up being. A thesis on quantum gravity. And actually, it's not causal fermion systems. And the more I read into causal fermion systems, I think, from an abstract, yet again, mathematical sort of way, I'm sure there's sort of these Borel measures and whatever. It does sort of work, to harmonize general relativity with quantum mechanics and whatnot. And it smushes the maths together to make something that seems legit come out of it. That seems like a good way of representing it. Very, very potential, sure. But I don't know. I like Lagrangians, and I like simple, ideas, just like particles swallowing other particles to make composite particles that look like another particle. I like all this idea. Shadow maths, I'll call it. I'll invent a new branch of mathematics called shadow maths. And the maths of deceit, or the logic of deception, and chameleon particles, particles that look like other particles or imitate their background or what have you. Yeah, I've looked at all sorts of lovely stuff. Can I not? Anyway, bye everyone. Love you lots. I'll see you soon. I got the wallpaper written and submitted and accepted at Nature and the Nobel Prize, obviously. And see you soon.